Have you ever been stuck in traffic and wondered how it all started? Nobody wakes up in the morning thinking, today I'm going to create a traffic jam. Every driver is simply trying to get somewhere, to work, to school, to an appointment, to home. Yet somehow, traffic jams appear every single day. Entire highways slow down, bottlenecks emerge, vehicles stop and start repeatedly. How can thousands of people, all trying to move efficiently, create such inefficient outcomes? The answer lies in one of the most fascinating ideas in physics: chaos.
When most people hear the word chaos, they think of randomness. But in physics, chaos means something much more interesting. Think about a crowded subway station. Thousands of people enter and leave the platform every minute. Yet recognizable patterns begin to appear. Crowds form lanes, bottlenecks develop, congestion grows and disappears. This phenomenon is called emergence, complex behavior created by many simple interactions.
Imagine ordering an Uber. The app tells you the driver will arrive in 5 minutes, sometimes earlier, sometimes later. A traffic light changes. A pedestrian crosses the road. A truck blocks a lane. A driver brakes unexpectedly. Small causes can produce surprisingly large effects.
Trying to track every individual driver would be nearly impossible, so physicists focus on the collective behavior of traffic. Instead of tracking every vehicle, we describe traffic using a few important variables. The first variable is density. Density tells us how crowded a region is. We represent density using the Greek letter rho. If only a few vehicles occupy a large area, density is low. If many vehicles are packed closely together, density is high. Density answers one simple question: how crowded is this part of the road?
When roads are empty, drivers travel near their maximum speed. As density increases, drivers must slow down. This relationship can be described using V of rho equals V max times 1 minus rho over rho max. Here, V of rho equals traffic speed. V max equals maximum speed. Rho equals current density. Rho max equals maximum density. As density increases, speed decreases. More cars mean less space. Less space means slower traffic.
So far, we've introduced two important quantities. Density tells us how busy the road is. Speed tells us how fast vehicles can move. Now we introduce a third quantity: traffic flow. Traffic flow measures how many vehicles pass through a section of road every second. J equals rho phi. Flow equals density multiplied by speed. The highest flow occurs somewhere between an empty road and a complete traffic jam.
Every driver has a destination. We represent the direction toward that destination using a direction vector d hat. This vector points from the driver's current position toward the desired destination. It only tells us direction, not speed.
Drivers also try to avoid congestion. The density gradient, delta rho, points toward regions of increasing density. The negative gradient, negative delta rho, points toward lower density. This naturally represents congestion avoidance.
Combining destination seeking and congestion avoidance gives V equals V max times 1 minus rho over rho max times d hat minus beta times change rho. The first term moves vehicles toward their destination. The second term pushes them away from crowded regions. Beta controls how strongly drivers avoid congestion.
Density affects velocity. Velocity changes traffic flow. Traffic flow changes density. The new density changes velocity again. This creates a feedback loop that drives complex behavior. To derive the differential equation that describes this system, we first need to apply the principle of flow conservation. Del rho over del t plus del dot rho v equals q of xyt. This equation tells us how density changes over time. Q represents cars entering and leaving the system through on-ramps, off-ramps, and intersections.
No driver is trying to create traffic jams. Every driver follows two simple rules: move towards the destination, avoid congestion. Yet when thousands of drivers follow these rules simultaneously, traffic waves, bottlenecks, and complex patterns emerge.
Now, we can bring everything together. The conservation equation tells us how traffic density changes over time. The velocity model tells us how drivers choose their movement. When we combine these two ideas, we obtain the complete traffic model. This single equation describes how traffic evolves across both space and time. Let's break it down. The first term measures how density changes at a specific location. The second term represents the movement or flux of vehicles through the system. The source term accounts for vehicles entering and leaving the system through on-ramps, off-ramps, and intersections. Together, these terms determine how traffic density evolves throughout the network. What makes this model powerful is that every component has a clear physical meaning. There is no randomness built into the equation. Each driver follows simple and understandable rules. And large-scale patterns arise from countless local decisions. This is the central idea of chaos theory. Simple rules can generate remarkably complex behavior. Traffic is only one example of a complex system. The same principles appear in crowd dynamics, financial markets, biological systems, and weather patterns. Chaos is not necessarily randomness. Complexity can emerge from simplicity. Order can emerge from chaos.